This is a Sutotal production. Alright, Chem Minions, this is going to act as our third and final practice video for Chapter 2. Here we're looking at acids / acid-base reactions. So one thing you need to kind of think of is how can you figure out what the strongest acid is. And so we talk a lot about what's the most polar bond you could have, specifically the most polar bond that a hydrogen possesses. And so if we look at this first set here, every hydrogen here is a carbon-hydrogen bond. That's what it's a part of. Those are non-polar bonds. Those aren't going to be very acidic. Now, these can act as acids, like in particular the hydrogens here and here could act acidic, but they would have to be under a very, very strong base condition. And the same thing goes for this one right here. That's a carbon-hydrogen bond, and then the rest of them are carbon-hydrogens. So there's nothing that just stands out and is very acidic. And so really what stands out here is the OH bond here and here. Both of those are acidic, but how can you tell which one of these is more acidic? Well, sometimes it works best if you look at it after you remove the hydrogen. So have this guy act like an acid, and so what would its conjugate base look like? It would have a negative oxygen here, right? Now, this guy also has the added benefit of, you notice you have a single bond and a double bond, and that oxygen has a negative charge. So this guy also has resonance. Like so. So this is resonance stabilized once it gets deprotonated. But if we look at this guy after it acts like an acid, it's just going to have a negative oxygen and there's no resonance structure. So based off that, we can assume that this is going to be the strongest acid of these four, right? Don't really have polar bonds to easily remove a hydrogen. They both had polar bonds. Resonance after deprotonization was the winner. Okay. Next up, we see a lot of the same stuff, like we see nothing but carbon-hydrogen bonds, because remember, the whole point of an acid, I forgot to say that, but the whole point of the acid is that it's going to donate protons, right? That's what they do. And so really that means the protons that we think about are H+. So we have to remove hydrogens from these structures. So nothing but carbon-hydrogen bonds, nothing but carbon-hydrogen single bonds. Oh, here we go. We now have the OH and the OH again. And if you notice, both of these are just like, they're very similar to this one, except now here at this second carbon position there's a fluorine, and then here there's an additional methyl group. Now, the importance here is fluorine is more electronegative than a carbon. Right, so what does that mean? That means that this fluorine is actually pulling electron density towards it. So both of these are resonance stabilized, but this one also has an electron withdrawing group, an electronegative atom that's going to weaken the OH bond even more, while this guy will actually strengthen the OH bond. So this is going to be our strongest, right? So using these electronegative atoms, right, that's called the inductive effect, okay? So inductive effect. Inductively, these electronegative groups, they weaken this OH bond and make it easier to break off, right? And the easier the hydrogen breaks off, the easier it is to donate protons, right? All right, next up we have nothing but carbon-hydrogen bonds. Oh, we have an OH bond here, and then nothing but carbon-hydrogen bonds, and then we have an OH there. So it's really between these two, because these two have the most polar bonds. And so when we look at them, we kind of have a similar thing going on here that we did up here, right? In this one, both of these are what we call alcohol functional groups, and we'll learn more about that in the next chapter. But these are alcohol functional groups. And so when this donates a proton, we go back to that same original oxygen with a negative charge. But then when we look at this guy, we still get an oxygen with a negative charge. But you notice, double bond, single bond, negative charge. This guy has resonance just like that guy did. So right? If we look at what the resonance could possibly look like, there's going to be multiple ones, but I'm just going to show the first one. Here you can see right, that is resonance stabilized, unlike this guy. So this conjugate base is a more stable base, aka that's going to be our strongest acid here. Okay, all right, so now looking at our second problem here, here we have equilibrium reactions, where these are more or less looking at acid-base reactions, and so we have to figure out the side that's favored. And so to remember what we talked about in class in terms of which side is going to be favored, it's always the weaker acid side that's favored or the weaker base side that's favored. So you think about it like this, right? We know that acids donate protons, right? The stronger the acid, the more it wants to donate that proton, right? So what does that tell us? That tells us that the conjugate base of strong acids are the most stable, all right? And so these first two are kind of an example of you can use pKa to tell you which side is favored. All right, so for instance, the two acids are told to us. We have this double bonded carbon here, this double bonded carbon-oxygen double bond here, which we're going to learn is a ketone, and then we also have this alcohol. And so based off the pKa value given, we can estimate the acid strength. Right, so the smaller the pKa value, the stronger the acid. So between these two, this is the smaller value, so this is the stronger acid, while this is the weaker acid. All right, and so remember, the weak side is always favored, so that would mean that this reaction is reactant favored. All right, now we come down here and we see a change. Right, now we're looking at a change where we still have the same ketone as before with a pKa of 19, but now our acid on the other side is ammonia, which has a pKa of 40. Right, that's a big number, which means that this is a super weak base. A super weak acid compared to our carbonyl here, compared to our ketone. So this is the weaker acid now, and this is the stronger acid. Right, and so the weak side, the weaker acid side, is the one that's favored. Okay, now one other way that we can kind of figure this out too is if you look at the conjugate bases. So this acid turns into this conjugate base. All right, but this conjugate base has resonance. We've already saw that previously, right? So, right, we know that that negative charge here can move, right, to give us this resonance structure, where now you also have a negative oxygen. So this is resonance stabilized, meaning this conjugate base is more stable than this one. That negative charge can't go anywhere. It can't go to those hydrogens. So sometimes too you can look at the conjugate bases, those things with negative charges, and you can estimate the favored side as well. So the side that has the most stable negative charge is the favored side, right? So that's why weaker acids are favored, because weaker acids are more stable than stronger acids. All right, now we look at this one right here, and we've got CH bond as the acid here, right? The negative charges are not our acids, right? Acids are proton donators. Protons are positively charged, so negatively charged stuff isn't going to act like our acids. So here we have only CH bonds, which are nonpolar. And then here we have an OH bond, which is polar. Right? So because we have a nonpolar bond versus a polar bond, this is going to be easier to break. Polar bonds mean the hydrogen is easier to break off. So I'm going to put polar. All of that, this comparison means this is the stronger acid, and then that makes this the weaker acid. All right, and remember, the weaker acid side is favored, so this is reactant favored. Okay, now yet again, remember I said you can always check the negative charges too. So if you notice here, you have a negative oxygen versus a negative carbon. Which one's more electronegative? Hopefully you said oxygen, because that would be correct. And so if your oxygen is more electronegative, it wants the negative charge, right? Way more than carbon does. So it also makes sense that, hey, I've got a conjugate base that makes more sense. The more electronegative atom has the negative charge. All right, looking here, let's find our acids. So the acids on either side would be this guy because we have an OH bond, which yet again we said was polar. And then here we have an HH bond. That's a non-polar bond. All right, and so same as before, right? Non-polar versus polar, which one's easier to break off the hydrogen? The polar bond. So this is the stronger acid, and then this is the weaker acid. All right, so between these two, you always pick the weaker acid side. So this tells us that this is product favored. All right, and then as a second round of checking, right, look at the negative charges. Negative oxygen versus negative hydrogen. Which one's more electronegative? Oxygen's more electronegative. So it makes sense. The more electronegative atom has the negative charge. So yet again, even the conjugate base here, this guy, is telling us that it's product favored. All right, so hopefully this gave you a good trip down acid lane. That doesn't sound right. Anyway, so hopefully this is helpful. I'll see y'all later, and stay weird.